4, we're going to talk about something called electron configuration. Okay, what does the word configuration mean?
Like the structure of how something's built up?
Yeah, how it's built up. What's another way we could describe that? Configuration. If we look at how something is configured, we're looking at how it's laid out, right? How it's arranged. Those are all ways we could describe the word configuration. So when we talk about electron, we're going to talk about the basic arrangement of an atom. So let me kind of give you the big goal of our chapter here, right? This chapter on electron configuration, by the end of the chapter, we will be able to give essentially the address of a single electron in an atom. Okay, we'll be able to give its location, what orbital it's located in, the section of the atom that it's located in. We're going to be able to talk about what direction is it spinning. We're going to be able to essentially give the address of a single electron within an atom. So we'll be able to say, let's look at potassium, for example. How many electrons does a neutral potassium atom have? It has 19, right? Because if it's neutral, it has the same number of electrons as protons. We agree with that? So if it has 19 electrons, I would be able to look and say, okay, the 12th electron that goes into potassium, it has an address of 1, 0, 0, negative 1/2, right? And so that number, that string of numbers I just gave you is considered its quantum number or its address. And so we're going to be able to give an address for every single electron that goes into an atom, right? And we're going to be able to kind of pinpoint its location in the atom, which when you think about it is a really cool, that's a really cool thing to be able to do because electrons are teeny, teeny, tiny. It's not like we can visibly see that, right? But based on the theory that we're able to study, we're able to kind of pinpoint the location of those electrons. So that's our goal. So we're going to start today with a little bit bigger picture of that, and then we'll kind of be able to dial in what that looks like. So we're going to start with electron configuration. And let's look back at a previous model of the atom. We talked first about what was the only kind of real model of the atom that we've studied so far? The guy that did the gold foil experiment. What was his name? The Rutherford model of the atom. And it looked like a planet, right? It had a nucleus in the middle, and then it had our electrons orbiting along the outside, right? That was the Rutherford model of the atom. After that came something called the Bohr model. And again, this is not what we use today, but this gives us our successive steps of how the atom has been studied. So the Bohr model says that electrons don't orbit the nucleus, but they circle them, right? It goes around kind of like a merry-go-round, right? They circle the nucleus, and they're only allowed in certain particular paths. What the Bohr model said is that electrons are in their lowest energy state when they orbit closest to the nucleus. So the closer to the nucleus the electrons are, the lower energy they are. And that is still true today. We know that to be true today. Electrons always want to find the lowest energy state they can. Okay? It's a really important model in the steps of what the atom looks like. Okay? So now we're going to get into what's called the quantum model, and that's really what we're going to study today. We're going to start with what we call the electron configuration. And electron configuration, like we said, is the arrangement of electrons in an atom, right? It's how they are arranged. Okay? They want to assume arrangements of the lowest possible energy. So they want to be kind of sit and tucked in safely into what we call an orbital. They don't want to be out on a limb or out in high energy places. They want to be in their lowest energy state possible. And we call those ground state electron configurations. Okay, they're at their lowest energy. We call them ground state electron configurations. And that's really what we're going to study. We're not going to study electron configurations of atoms that are doing abnormal things. We're really going to study kind of the rule. And then when you get to higher level chemistry classes, you might study the exceptions. But for right now, we're studying what do most atoms do most of the time, right? We're following the rule. And so that's what we say when we mean that's what we mean when we say ground state electron configurations. We're going to determine the ground state electron configuration for every element. Right? We'll be able to know how are the electrons arranged in all of our elements, and it follows a pattern. The first thing that so what to do is I want to talk about the periodic table and how it mirrors electron configurations. Okay, how it mirrors electron configurations. So I want you to get your periodic table out for me. And I want you to kind of look at the periodic table for me in this way. Okay, it says that these two groups are in what we consider the S block. Okay, elements in these first two groups are considered the S block. Okay, and I'm going to explain what they mean here in just a minute, but I want us to kind of get some labels down first. If you want to label this on your periodic table, you can. This right here is called the D block, right? These two are S, D. The middle section right here is considered the, I did the second one wrong. That's my fault. This one is P. I don't know what I was thinking. This is the P, D, and then our bottom two groups down here are called the F block. Okay, I will explain what these mean here in just a second, but I want us to give these labels on our periodic table first. Okay, so these two groups right here are considered the S block. P, So S, these ones right here, these blue ones. P is all of these elements right here. Okay, that's the P block. D block is the transition metals right here in the middle. That's the D. D is in the middle, And then F is the lanthanides and the actinide series down on the bottom. Okay. Now, I want us to get a picture of what do we mean when we say S block, P, D, and F. When we talk about S, P, D, and F, okay, and when we talk about an element's electron configuration, when we say we're going to do the electron configuration for sodium, what we're really talking about is we're finding the electron configuration, the arrangement of the last electron to get placed in our sodium atom. Okay, so tell me again, if I'm looking at sodium, how many electrons does sodium have?
11.
It has 11, right? Because a neutral sodium atom has 11 electrons. And so when I say I want the electron configuration for sodium, what I'm really saying is I want the electron configuration for electron number 11, the last one to get placed into sodium. Does that make sense? And so if I'm saying that I want the electron configuration for sodium or the last electron in sodium, I know that the last electron placed in sodium is going to be in what we call an s orbital. Okay, because sodium is found in the s block. Okay, so that means if I'm looking at the last electron for sodium, it is in what we consider an s orbital. And again, I'll explain these a little bit more as we go on. I know this seems like a little bit crazy right now, but I'll explain as we go. The last electron found in sodium is in what we consider an s orbital. So what if I asked you the same question about cobalt? Where would cobalt's last electron be located, and what type of orbital? It would be in a d orbital, because that element is found in the d block. Okay, so the last electron to go in cobalt, number 27, it would be in what we consider the d orbital. What would be true about fluorine's last electron? What type of an orbital would it be in? A p. Yeah, fluorine is found in the p block, so that means that fluorine's last electron is in what we call a p orbital. And now I hope you're asking the question like, well, what is an orbital? Right? An orbital, and I want you to write this down. An orbital, okay, it is basic. Yeah, I want you to write it down. It's basically an electron pocket, okay? And it's definitely not the textbook definition of that, but that's what I think of it as, okay? It's an electron pocket. It's what contains the electrons. Okay, it's what contains the electrons.
Write it on the periodic table?
No, in your notes probably. In your notes, sorry. Your notes has this slide too. Okay. It does. Okay, it's what we consider an electron pocket. And each individual orbital can only hold 2 electrons. Okay, I'll explain that a little bit more later, but each electron orbital can only hold 2 electrons. Okay, so we'll talk through some more information with that here in just a minute, but orbitals are basically electron pockets, and each orbital can hold 2 electrons. If we know that each orbital can only hold 2 electrons, there has to be some atoms that have a lot of orbitals, don't there? Yeah. Right? Because how can I get all of cobalt's 27 electrons in if each orbital can only hold 2 electrons? There has to be tons of versions of these orbitals. Would we agree? Okay, and that's true. They have different shapes. They're on different levels. They're arranged different ways, and so that's what we're going to kind of look at next, okay? So we know that our orbitals are electron pockets or electron holders, and they can hold 2 electrons. I'm going to skip over this, and I'm going to come back to it. And let's look at how do we know where our electrons can be located, okay? I want you to label your periodic table the periods, which go downward, okay? They kind of got shifted on this slide. I apologize. This is period 1, 2, 3, 4, 5, 6, and 7. Do you see how that is labeled there? Yeah. Okay, I want you to label those just off to the side, probably, 1 through 7 on your periodic table. Okay, I want you to label 1 through 7 on your periodic table. So we know this is period 1, period 2, period 3, all the way down to 7. Okay? What we know about our atom and the model of the atom is that every time we start over, every time our periodic table drops down to the next row, right here, that means we add another shell. We add another level of atoms. And so every time, like when we go from hydrogen and helium and we come down to lithium, we add a new s orbital. So a new sphere envelops that atom. Then we add electrons in the p orbitals, and then we start over again. So when we go from neon down here to sodium, we add a whole nother sphere on top of that, and our atom just keeps getting bigger and bigger and bigger, right? We keep adding electrons to that, but every time we move down a row on the periodic table, we get one more layer to our atom, okay? And so the way we read this is that these electrons in hydrogen are in what we call the 1s orbital. They're in level 1, and they're in the s orbital. Does that make sense? Level 1, s orbital. If we come down to lithium, right here, this is where it would be on the periodic table, it's in the 2nd level, and it's in the s block. So we would call these 2s orbital. Okay? And then we move across the periodic table, and we have a p orbital in this level, so we call it 2p. Okay, do you see how that pattern works and how we can follow the periodic table to do that? We come down to the 3rd level s orbital, we call it 3s. We move over, and 3p. So if I wanted to find out what orbital chlorine's last electron is in, I'm going to come over to chlorine and I'm going to count. 1, 2, 3. It's in the 3rd level. Would we agree with that? Mm-hmm. 3rd level. And what block is it in? P. P. So chlorine's last electron would be found in a 3p orbital. So it would be the 3rd energy level, the 3rd shell, and it would be in one of the shapes that are like that propeller shape, right? That would be where it would be located. Are we doing okay with that so far? Yeah. Okay, so here's where we throw kind of a wrench in our system, is that when we get to the d orbitals, they actually are supposed to fit on the 3rd level, but the periodic table doesn't work like that. And so we go from 4s to then 3d. So that's a little bit of a shift, right? Instead of being 4D right here, because it's in the 4th level, it's actually labeled 3D. So there's a shift right there. So that's just something that you have to remember, okay? The D orbitals had been moved down 1 as to where they were supposed to be. So you'll need to remember that elements in this, right here are 3D. So then it'd be 3, 4, 5, and 6, okay? The same thing happens with the F orbital, but they're shifted actually 2. So they're supposed to fit right up here. And so after 6 goes 4F, and then we move back from there. Okay? Okay, so let me tell you that when we're looking for electron configurations and we're trying to write it out, we have to represent every electron. Even though we're trying to find, maybe the last electron in that atom, We still have to write every one of them out. So we will just follow the periodic table to fill in all of our electrons until we get to the one we want. Okay, so I'll kind of walk you through that as we go here. But are we doing okay? Hanging in there so far? Okay, let's look at electron shapes right here. Okay, so here are the orbitals that we were just talking about. An s orbital can hold 2 electrons, and it's shaped just like this. It's just a sphere that surrounds the nucleus. And so the 2 electrons that are located in an s orbital just exist within that sphere. They can bounce around anywhere they want to within that sphere. Okay? So those are really kind of simple, okay? And I want you to kind of look at this S block, and you can remember it like this. The S block has how many groups in it? 2. So this S orbital can hold 2 electrons, okay? There's one version of the S orbital, and it can hold 2 electrons. Okay, next one is the P orbital, and it sits on this side of the periodic table, isn't there? It sits over here. How many groups do we have in the P block? 1, 2, 3, 4, 5, 6. Okay, so we have basically 6 electrons that need to go in the P orbitals. But we said each orbital can only hold 2. So how many versions of the P orbitals do we need to have?
3.
We need to have 3 versions. And so this is what it looks like. There's a P orbital that looks kind of like this. I don't even know what you'd call that. I don't know what shape it is, but we're going to have 3 versions of it. 1, 2, and 3, right? Here's one version, here's another version, here's another version, and they fit together just like that. So this would be 1 electron, 1 electron, 1 electron, another, right? There's where our 6 electrons can sit in the P orbitals. We have 3 different versions. 1, 2, and 3.
Do it again.
Okay? There's one version of our P orbital. There's 2 electrons. Yeah, it kind of looks like a propeller, right? There's 2, the second version, there's our 2 electrons, and there's the third version. It just kind of depends on how they're oriented around the nucleus, right? They fit together around that nucleus. But the way we can remember this is on the periodic table. The periodic table shadows a lot of the patterns that we need to see. We know that the P block has 6 groups in it. 1, 2, 3, 4, 5, 6. So the P orbitals can hold a total of 6 electrons. Right? Those 2 things mimic each other. That's just a pattern that is represented on the periodic table. Okay, are we feeling okay so far?
Something like that.
Yeah, go ahead.
These orbitals, do they just represent like the outermost shell of the?
Yeah, okay, so a little bit. What happens is after we fill an s orbital, and then the p orbitals go around it, and then the d orbitals go around that. So it makes this big cluster, and then when it's time to get a new row, another s orbital envelops that. So it just keeps building outward. Yeah. Okay, the next one is called the d orbitals, and there are 1, 2, 3, 4, and 5 versions of the p orbitals. This is what it looks like when they all go together. That's crazy looking, isn't it?
Yeah.
Right, that's just crazy. And these are not like hard lines. They're just kind of little areas that hold our electrons in. But if there's 5 versions of our orbitals that can each hold 2, how many electrons can the d orbitals hold in total? 10. And so count here. This is the d block, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? That pattern is mimicked on the periodic table. So if you're unsure about how many electrons can fit in the d orbitals, just count across, right? That means 10 total. So there must be 5 versions of that. Okay, I'm not going to ask you to ever draw out these d orbitals because look how many versions and look how crazy they look, right? This version itself can only hold 2 electrons. So that means 2 of these are empty. Okay, so it's just like, it's very kind of arbitrary. And these are not like hard lines, right? We just have done a lot of experiments that find them like electron locators. And so they're usually located within this little shape, right? And so that's why they made it that shape.
Why does 1 hold 2?
Which one?
1.
Each of our orbital shapes can hold 2 electrons. Okay, and so they could be found anywhere within that shape. Okay? The F orbitals, I didn't even draw them up here because they're so crazy looking. How many versions of the F orbitals do we think there are? Let's count the F block. There's how many?
14.
There's 14 elements in the F block. So how many versions of the F orbitals do there need to be? There's going to have to be 7. Okay. Now, for us, we very rarely even get into dealing with the F orbitals. We maybe look at the D orbitals every once in a while, but we don't get into the F orbital very much, which is great. Okay? So do you have a little bit of an idea of what's happening here?
Yes, ma'am.
Okay, I know it's very arbitrary. I promise once we practice some, it will click a little bit more. Okay, but I want to show us the patterns that happen on the periodic table. Okay, so let's go back one slide. Let's look at, this is a little kind of a cheat sheet. It tells us the order in which our electron orbitals have to be filled. When electrons fall into an atom, they have to go in an order. They can't just go in like willy-nilly and sit wherever they want to. They have to go in the 1s orbital first, and then they fill up the 2s orbital, and then they fill up 2p, right? And for me, I like to follow it on the periodic table. But some people don't necessarily like to see that pattern, right? For me, it makes sense that if my electrons go in order, they're going to go in order of the 1s orbitals, and then I'm empty. And then I come down and I fill the 2s orbitals right here, and then I move across to the 2p. And then I go over to 3s, and then 3p, and then 4s, right? I like to follow the periodic table. Some people don't like that as much. So if we follow this chart, it tells me the 1s orbitals go first, then the 2s orbitals, then 2p, then 3s, then 3p, then 4s, then 3d, 4p, 5s, right? It tells you the order you need to go in. If you don't like this, then don't worry about it. If this makes more sense to you, then let me know and I can print one of these out for you. Okay? But it gives us just literally a graph we can follow. We just follow the arrow. That tells us the order and that our electrons need to be filled in. Okay? But you could also just follow it right along the periodic table. It's the same.
Would we be able to have that on a test?
This is something you can use on the test, and your periodic table obviously you'll be able to use on the test too. So I'll let you decide if you want one of these. I can print the out for you a little bit bigger if you want.
But I don't
Okay.
understand.
It was not supposed to be.
This just tells us the order in which our electron orbitals have to be filled. So it's telling us we have to fill up the 1s orbital before we can move to fill up the 2s orbital. And then after that comes the 2p orbital. So it tells us the order, but our periodic table tells us the same thing. We have to fill 1s, and then we start over at 2s, and then we move across to 2p, and then we go down to 3s, right? It tells us the same information, but some people like to see it here, and some people like to use this little cheat sheet, a little graphic organizer. I don't know. You can use whatever you want. Okay? So let's go ahead and try one here. Okay? I want you to look at how these electron configurations are laid out. Okay, I just want to show you, these are the electron configurations for several of our first atoms. And I want to just kind of look at them and compare them. Okay, so let's start with a simple one, hydrogen.
1s.
Hydrogen has only one electron. And we said it's in what type of an orbital?
S.
Yep, and it's in what energy level? 1. Okay, so its configuration is literally just this, 1s, and then up here as a kind of an exponent, a superscript, you write a 1 because it tells us it has one electron in that 1s orbital. Right? And that's it. That's its electron configuration right there. Pretty simple, right? If we move over to helium, right? Helium sits technically in the p block, but in all reality, its electron is only, it's an s, because it has to fill the s orbitals first, and there's no such thing as a 1p orbital. There's no such thing as that. So even though helium sits on that side of the periodic table, it's actually part of the s block. That one's a little bit tricky, but helium has 2 electrons. So its electrons are found in the 1s block, and it has 2 electrons found in there. Right, because it only has 2 electrons, and they have to go into the s orbital. Okay, let's skip ahead a little bit. Let's try oxygen.
16.
Let's try oxygen. So oxygen's last electron is found where? It's found in the p block. Is it 1p, 2p, 3p?
2p.
Okay, it's going to be 2p something.
2p8.
Not quite, not 2p8. Okay, let's just wait just a second. But before we can even get to 2p, we have to fill all of the previous orbitals. So in order to get to oxygen, don't we have to fill the 1s block? We do. So oxygen's electron configuration looks like this. 1s, and how many electrons can fit in there?
6.
In the S block, just 2. That's okay. Jump down now. Is there anything such as a 1p? No. So after 1s, where do I go? I come across here and I start at 2s. Is that electron orbital full? In order to get to oxygen, I have to fill that one, right? So how many electrons can go in 2s? 2. And then we said oxygen is in the 2p orbital. I agree, right? So I'm just going to count over. Oxygen is the 1, 2, 3, 4th element in that block. So it has 4 electrons in that 2p orbital.
That's what I say. 4. That was right.
It adds up to 8.
No, I
That's
do.
just pure numbers.
No, I do 2, 6.
Okay, here's how we check our answer. Excuse me. Here's how we check our answer. We count up our electrons. 2 plus 2 plus 4 gives us how many electrons? 8. And isn't that what oxygen's supposed to have?
Yes, no.
It is. That's exactly what we're supposed to have.
Okay, how did you get a 2s2?
So in order to get to oxygen on the periodic table, I had to fill the 1s orbitals, right? That can hold 2 electrons. That was now full, and I had to move down to here. And so I had to fill these 2s orbitals before I can move over and get to oxygen.
Oh, that's a number 2?
That's a number 2.
Oh, that was a Z on the
Nope, it's a 2. Second energy level, s orbital is full. So it's going to s2. And then I'm going to come over to oxygen, and I'm going to count. It's the 1, 2, 3, 4th element in that block.
Okay.
When you says 2 people,
Uh-huh.
you start off at beryllium.
I start off at boron. I start in the p orbitals, and I say boron would be 2p1, carbon would be 2p2, nitrogen would be 2p3, oxygen would be 2p4. Right? So how would nitrogen's electron configuration be different than oxygen's?
Because nitrogen is only the 3.
Right, so does the first part of it look the same though?
Yes.
It would look the same. 1s2, 2s2, 2p3, right? And our electrons here would add up to 7 for nitrogen. Okay? I know it seems crazy when I first start talking about it, but once we get into the examples, I think it becomes a little bit easier. Okay? Let's try magnesium. Let's try magnesium. Yeah.
What's the first one?
This was just talking about oxygen is going to be in the 2p. So that's not a finished electron configuration. No. Let's look at magnesium. Magnesium is Mg. Okay, okay, so first of all, tell me, where do we need to end up with magnesium? We need to end up at 3s, which means we have to fill everything up until that point. So we have to fill the 1s orbitals with 2 electrons. We have to fill the 2s orbitals with 2 electrons. Where do we move after 2s? We move across to 2p, and how many can it hold? 6, right? And then after 2p, we move down to 3s. And how many electrons would magnesium have there? 2, right? And so then we can count. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12 electrons. And is that what we're supposed to have? Very
You need to print that one.
okay, we can do that. All right, let's look at a few more of our electron configurations. Let's look at potassium. Potassium. Let's find potassium first and figure out. I think it's good for us to know where we're trying to end up here. We're trying to end up at 4 what? 4s. So in order to get to 4s, we need to fill all of the previous ones. So 1s with 2 electrons, 2s with 2 electrons, 2p, it can hold 6 electrons. Then we go 3s, can hold 2 electrons. From there, do we go to 3d?
3p.
We go to 3p, right? We skip over there because we're not in the d orbitals yet. We go to 3p. How many can it hold? 6. And then from there, we go to 4s, not 4s2, 4s1. 4s1, because K is the first element in that book. You could, but that would be if I was doing calcium. Yeah. Not for potassium. Potassium is supposed to have 19. So we could count them and say 2 plus 2 is 4. That's 10, 12, 18, 19.
So the second one, we should just have the same thing as before.
Exactly. For calcium then, my next one, everything here would look the same. right? 1s2, 2s2, 2p6, 3s2, 3p, and 4s2. Yep, everything else would look the same except it would be 4s2. So here's the thing. When I ask for electron configuration, you have to give me the whole thing. You can't just write that. You have to give me the whole thing. You got to write it all the way out.
Sounds good.
Uh-huh.
Helium is S, but it's
That's right. It sits in the p block, but really its electrons are in the s orbital. Yep. So there's not ever such a thing as 1p. There's no 1p orbitals. It's just. Do you want to try silicon?
Yeah.
All right, let's do it.
Oh, shoot.
So silicon's going to end up where? 3p. Okay, so let's keep going. So we're going to go 1s2, 2s2, 2p6, 3s2, and 3p what? 3p2.
say RH.
Which one?
Mine say RH.
Oh, sorry. I must have changed it on the slides. We can do that one too.
Where?
On the slide, I must have put in a different element there.
AMSI.
I got RH.
I have RH.
Go RH.
Fifth column.
Oops. Okay, RH is way down here, number 45. So that means we're gonna have a kind of a long electron configuration here. So let's follow along with what we need. 1s2, 2p. Oh, sorry. Yeah, sorry. 2s2, 2p6. Are we following along on our periodic table where we're at so far? 2p6. We just finished with like neon. Okay, so now we're gonna go down to sodium magnesium. That's 3s2, 3p6. So now we've just finished like at argon. Okay, so now we're down to potassium, 4s2. Where do we go after that? 3d. We just finished calcium right here. So we have to get through the d orbitals, and we know those aren't 4d, those are shifted up one. So those are going to be 3d and how many?
7.
No, not 7.
14.
10, right? It can hold 10. And if you can't remember, just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3d, 10. So after 3d, where do I go?
4P.
4p.
And that's what we
1, 2, 3, 4, 5, 6. So 4p6. I got to keep going.
5S.
Good. 5s2. I know it's
4D.
we're close. We're close. After that, where are we going?
We have 4D.
4.
D.
And then how many?
10.
1, 2, 3, 4, 5, 6,
Now we have
7. Don't we need to stop at RH? So we need to count. 1, 2, 3, 4, 5, 6, 7. So 4d7. Yes, no?
That one was
in RH.
So for RH, for rhodium, we went all the way to 4d7, right? Got kind of a little bit crazy right in there. We were in 3, 4, and 5, but we did a good job. Okay, so now I'm going to show you how we can abbreviate it. How can we make it so that we don't have to write such long electron configurations with something called the abbreviated electron configurations. We do that with a noble gas. Which group is the noble gases?
Helium and all of them.
Good. Helium, neon, argon. Why do you think we're going to abbreviate using the noble gases? Why are they special?
Because they are gases.
True, but that's not why they're special. They're at the end. Also true, not why they're special.
They're complete.
They have full shells, right? Their p orbitals and their s orbitals are full, right? We just said s2 and p6. Those orbitals would be full for neon, argon, krypton, all of those. Agreed? Right? They would have a full shell. So we're right on the brink of then adding another shell to our electron. So we abbreviate them with the noble gas. So let's try calcium's abbreviated noble gas configuration. If I'm looking at calcium, it's number 20. I need to go back and find what's the noble gas that comes before calcium?
Argon.
Argon. Okay, so if I'm looking at calcium's electron configuration, argon is the noble gas that comes before that. So I'm going to put it into brackets. And I'm going to say it's the same configuration as argon, plus whatever comes after that to get to calcium. So after argon, I would have to add on what to get to calcium? 4s2.
4S2.
right? It's like me taking out all of the 1s2, 2s2, 2p6, 3s2, 3p6, right? I take all of that out and I abbreviate it and say it's the same configuration as argon plus the extra. Okay, so that's a lot quicker than writing it all out, isn't it?
Yes, I know, like,
Okay.
just have to keep writing stuff.
Okay.
That's okay.
Again,
You'll be asked for both. Sometimes I'll ask for the electron configuration. That means you got to give me the whole thing. And sometimes they'll ask you for the abbreviated. Or another word for this one is called the noble gas configuration. And that's because you're using a noble gas. Okay? Let's try the abbreviated configuration for iron. Okay, do you find iron? It's number 26.
number 26.
So iron, we have to find the,
Again.
it's argon that comes before it.
And the 3D.
Okay, but we can't just put 3D something because that skipped over what?
4P, 4S.
It skipped over 4S. So it's argon plus everything that comes after it. You can't just write its last part of its configuration. You got to write everything that comes after it. So argon, it would be 4S2. 3, you're right. 3D what?
1, 2, 3, 4, 5, 6.
3D6.
2 plus 6 plus 2.
Yeah, so you would count argon's electrons, which are 18, plus 8 more gives you 26. So that's a way you could check your electrons.
Are we always,
That's D3, right?
Right.
The top one. So,
3D.
so
What are we
why would
talking-
argon? Why would you put that after argon since it's technically before argon in the periodic table?
Right, okay, so even though they're in the third energy level, they don't open up until the fourth.
Okay.
So it's a weird kind of difference there. But the d orbitals, okay, let me say that again. The d orbitals become available in the third level. That's why they're called 3D. But they don't actually get filled. Electrons don't start going in there until after 4s. So they become available at level 3, but they don't actually start getting filled until after 4s. And so that's just something that is a weird thing. You will see some things like CK12, sometimes it puts 3D up in that order, like after 3P. It's okay. It's not necessarily wrong. It's just not the way that we usually do it. Yeah. Okay. Yeah.
Are we always supposed to
Argon in brackets, it'll be whatever noble gas comes before that. So let's do strontium. Let's do SR. Okay, so if I'm looking at the abbreviated configuration for SR, what's the noble gas that comes before that? Kr. So for strontium, we would say krypton in brackets, and then we would say 5s2. So it's not necessarily argon, it's whatever noble gas comes before that.
5S2.
Couple reminders here. You cannot abbreviate something with itself. So if I said give the abbreviated configuration for krypton, you can't just say krypton. You would have to go argon plus 4s2, 3d10, 4p6. Right? You can't abbreviate, like you can't give the definition of a word with itself.
Hold on, but I thought
Right.
the gas before